Hello students, in this video, let's revise some previous year board questions from the chapter Magnetic Effects of Electric Current. Before starting these questions, let me remind you that in this chapter, you have to be thorough with the following concepts. First of all, you should be well thorough with the diagrams where you have to show the magnetic field around a bar magnet, a straight current carrying conductor, a circular loop, solenoid. Be clear with the laws or rules that include the right hand thumb rule and Fleming's left hand rule. Then be thorough with the connections in a domestic circuit and the difference between AC and DC. If you are thorough with these concepts, then you be sure that you can crack any question that comes from this chapter. So let's move on to the questions. The first question is, an alpha particle enters a magnetic field at right angle to it as shown in the figure. Explain with the help of a relevant rule the direction of force acting on the alpha particle. Let's remember that in order to find the direction of force acting on a charged particle, we have to apply the Fleming's left hand rule. According to Fleming's left hand rule, if you release your thumb, forefinger and middle finger of the left hand mutually perpendicular to each other, then if the forefinger shows the direction of the magnetic field, central finger shows the direction of the current, then the thumb shows the direction of the force acting on the conductor or on the charged particle. Here in the question, the direction of magnetic field and the direction of current is given. How do you know the direction of the current? You know that alpha particle is a charged particle and flow of charge is actually electric current. Now, alpha particle is a positively charged particle. So, conventionally, the direction of current is also the same, that is the direction of the flow of the alpha particles. Here, the direction of flow of alpha particles is towards east or from left to right, and the direction of the magnetic field is towards north. Now release the forefinger and the middle finger which shows the direction of magnetic field and current as shown in the figure in your screen, in the right hand side of your screen, and release the thumb. To which direction does your thumb points? Yes, you can see that the thumb points towards upward direction. So the direction of force on the alpha particle is in the upward direction as per Fleming's left hand rule. So you have taken Fleming's left hand rule to solve this question. Moving on to the second question. Mention the shape of magnetic field lines around a current carrying straight conductor. The magnetic field lines around a current carrying straight conductor is found out by using the right hand thumb rule. The rule states that if you hold a current carrying straight conductor with your right hand in such a way that the thumb shows the direction of the current, then the wrapped finger shows the direction of the magnetic field. So on applying the right hand thumb rule, we can understand that the magnetic field lines around a current carrying straight conductor are in the form of concentric circular rings around the conductor. Question number 3. Identify the poles of the magnet in the given figure and state the direction of the magnetic field inside the bar magnet. To solve this question, let's recall the properties of magnetic field lines. From the properties of magnetic field lines, we can understand that magnetic field lines move from the north pole of a magnet to the south pole of a magnet outside the magnet. So now let's come back to the question. In the question, you can see that outside the magnet, the magnetic field lines are moving from B1 to A1. That means B1 is the north pole and A1 is the south pole of the magnet. And the direction of the magnetic field inside the bar magnet is from the south pole to the north pole. Question number 4. State the observation made by Oersted on the basis of his experiments with current carrying conductors. Let's recollect the experiment done by Oersted for understanding the magnetic effects of electric current. In this experiment, a magnetic compass needle is kept near a simple circuit. The circuit as of now is open and no current flows through the circuit. So when there is no current flowing through the circuit, the magnetic compass needle doesn't show any kind of change or any deflection. After this, the key is plugged on and the circuit becomes closed. When the circuit becomes closed, current starts flowing through the circuit. And as the current starts flowing through the circuit, the magnetic needle shows a deflection in the particular direction. When the circuit is again made open, the needle comes back to its original position. So this shows that when there is a flow of current, a magnetic field is produced around the current carrying conductor. So this was the first observation made by Oersted. He also observed that when the polarity is reversed, that is, the polarity of the battery is reversed, the direction of the current change, and this results in the change in the direction of deflection in the magnetic compass needle also. That means when the direction of current changes, the direction of magnetic field also changes. He also observed that when the magnetic compass was brought near to the conductor, the deflection of the needle increased, and when the magnetic compass needle was taken away from the conductor, the deflection of the needle decreased. The deflection in the needle was also seen to be increased when there was an increase in the magnitude of the current. So now let's summarize the observations made by Oersted in his experiment. The first observation was a magnetic field is produced near a current carrying conductor which lasts so long till there is a current in the conductor. On reversing the current, the direction of the field also reverses. When the compass needle was introduced close to the current carrying wire, the needle's deflection increases, and these observations led him to conclude that a current carrying conductor acts as a magnet. Moving on to question number 5. Find the direction of magnetic field due to a current carrying circular coil held vertically in north-south plane, and an observer looking it from east sees the current to flow in the anti-clockwise direction. So first let's keep the current carrying circular coil in the north-south direction, and the observer is looking from the east. Now the current is flowing in the anti-clockwise direction. We know that we can find the direction of magnetic field using the right hand thumb rule, and from the right hand thumb rule we can see that the magnetic field is directed from west to east in both the sides of the circular coil. So the direction of the magnetic field here is west to east. Second question, vertically in east-west plane, and an observer looking it from south sees the current to flow in the anti-clockwise direction. Now you can see that I have just changed the directions here, north-south and east-west, and it is vertically kept in east-west direction. The observer is looking from the south, so again use the right hand thumb rule, and you can see that the direction of the magnetic field is from north to south in both the ends of the circular coil. Horizontally, and an observer looking at it from below sees current to flow in the clockwise direction. So now the coil is kept horizontally and the observer is looking from the below, and the current is flowing in the clockwise direction. So apply the right hand thumb rule, and you can see that the direction of the magnetic field is upwards in both the case, or into the paper. If it is kept on a paper, you can say that the magnetic field is going into the paper. Question number 6. Justify the following statements. Two magnetic field lines never intersect with each other, and magnetic field lines are closed curves. We know that magnetic field lines always have a single direction, and that direction is obtained by drawing a tangent to the magnetic field line at that point, and the direction of the tangent is always in a single direction. So if two magnetic field lines intersect, it means at that point, if we can draw two tangents, that means at that point the magnetic field lines will have two different directions, which is not at all possible. So magnetic field lines never intersect with each other because it is always flowing from the north pole to the south pole of a magnet. Magnetic field lines are closed curve. It is always taken that field lines emerge from the north pole and merge at the south pole, and inside the magnet the direction of field lines is from the south pole to north pole, and they never intersect also. So these field lines are always forming a closed curve. Question number 7. Give reason for the following. There is either convergence or a divergence of magnetic field lines near the ends of a current carrying straight solenoid. The current carrying solenoid, when suspended freely, rests along a particular direction. We know that there is either a convergence or divergence of the magnetic field lines near the ends of a current carrying straight solenoid because it behaves similar to that of a bar magnet. That is, the magnetic field line pattern of a solenoid is similar to that of the pattern seen in a bar magnet. So in a bar magnet, when there is a converging end, that is a south pole is present, the lines converge at the south pole, and it seems like they are diverging from the north pole. For the second sub-question also, the reason is same. We know that when a bar magnet is suspended freely, it rests along the north-south direction. So we have already seen that a current carrying solenoid behaves similar to that of a bar magnet. So when it is also suspended freely, it will also rest in the north-south direction, or it will show any particular direction when suspended freely. Question number 8. Diagram shows the lengthwise section of a current carrying solenoid. Cross indicates current entering into the page and dots indicate current emerging out of the page. Decide which end of the solenoid, A or B, will behave as a north pole. Give reason for your answer. Also draw free lines inside the solenoid. To find the poles of a solenoid, we have to understand the clock phase rule. According to the clock phase rule, if the direction of current in the phase of a circular wire is in anti-clockwise, then that phase will act as a north pole, and if the direction of the current in the phase of a circular wire is clockwise, then that phase will act as a south pole. Now let's see the direction of current at the ends A and B of the solenoid. You can observe that at the end A, the current flows in anti-clockwise direction if you are observing it from end A, and if you observe it from end B, the current flows in the clockwise direction at the end B. So remember the clock phase rule. It is said that if the current is flowing in the anti-clockwise direction, then that phase acts as a north pole, and if the current is flowing in the clockwise direction, that phase acts as a south pole. So here in the solenoid, A is the north pole and B is the south pole. So if A and B are north and south pole, then you can draw the magnetic field lines of the solenoid as shown in the figure. The field lines emerge from A and enters through B. You can write the clock phase rule as the reason for your answer. So these are the 8 questions that I had decided to discuss in this video. Hope you all have understood all the 8 questions and how to solve these 8 questions, and note down these questions and answer in your physics note. If you like this video, then hit the like button and share the video among your friends and family. Also, check the link for the playlist of physics and chemistry chapters, as well as the links for the board exam revision like MCQs, assertion, reason, case study, etc., which is given in the description. Do show your love and support by subscribing the channel. Wait for part 2 video of the same chapter, where we are again going to discuss 8 more questions.